All right, so what we're going to start doing now is we're going to use geometric shapes to approximate areas. So if we think about that last example we did, we found the area under the x squared curve between 1 and 2, and we couldn't do that using geometric shapes that we know. But what we can do is break it up into shapes that we know and get pretty close. All right, so here's what that's going to look like, just kind of a general idea. If I wanted to find the area under this curve, say from x equals a to x equals b, this is not a geometric shape that is familiar to me. So to find the area of this thing, I'm going to have to get creative. So I want to find the area between x equals a, x equals b. I'm going to, hold on, let me draw this a little more accurately. So what I'm going to do to find this area is I'm going to break it up into shapes that I do know. All right, so one way to do this, and this is actually something that you guys did when we did the problem with the water tank, like first day of school, I'm going to break it up into rectangles. So I'm going to say, okay, let's just use 2 rectangles here. And so I'm going to make those rectangles kind of fit in this shape here. And I know how to find the area of these 2 rectangles. And I can even use the function to find the height of the rectangle at these 2 points. So I could say, okay, I want to split it up halfway between A and B. So if I find the average of A and B, that'll be the x value. I can use the distance here as the width. I can use the distance here as the width and find the area of those rectangles. Now we can see here immediately that, well, it'll approximate the area, but what? It's not very close, right? We're missing a bunch. All right, so we have some options. We could, instead of breaking it up into 2 rectangles, say break it up into 4 rectangles. And say, okay, with more rectangles, those gaps are going to be smaller. So I can find the area of rectangles like this. Okay, so with 4 rectangles, now finding the areas of these 4 rectangles, which is going to be twice as much work for me because I have to find the area of twice as many rectangles, but it's going to be more accurate. I'm still missing some. I've got some gaps here that I'm not going to get, but it's going to be closer. Okay, and what could I do to get even closer? More rectangles, right? Another thing that we could do, and this is not going to be very practical, but we could start filling this space with just smaller shapes. So I could just say, okay, I'm going to put another rectangle here. I'm going to put another rectangle here. This would get really messy if we were actually going to have to do this, because if we were to do that, then we'd have to find the width of each of these rectangles and then the height of those rectangles, which is going to depend on the height of these rectangles, and that would just get kind of nasty. But we could start filling these shapes. Okay, now this method kind of works, well, it works with the assumption that we're just going to fill it with more and more shapes inside of that area. But we could do the same thing, but instead of using rectangles inside, we could use rectangles outside. So we could use these rectangles here. And this would approximate it, but it would have a little bit extra then, right? Okay, and just like the last one, the more and more rectangles we use, the closer and closer we're going to get, but we're still going to be a little bit off. We're always going to have a little bit extra here. All right? And the reason we have extra, what we're doing is we're using the right endpoint of each interval as the top of the rectangle. And since this function is increasing, the right endpoint is higher than the left endpoint. So maybe instead of using rectangles, the right endpoint, or the left endpoint, which is always going to be less for this increasing function, maybe I could say I'm going to use the midpoint. And say, okay, right here at the midpoint, I'm going to use this as the height of my rectangle, and this midpoint here, and this midpoint here, and this midpoint here. And then when I do that, my rectangles are going to be a little bit above and a little bit below. Now, do you think this is going to give me the exact right answer? It's not. It'd be nice if it did, but it's not. And the reason is the over-approximating part here and the under-approximating part here, they're not going to be the same size. For this particular function, this region here is going to be a little bit bigger than this region here. Okay, now we don't have to worry about why that is or exactly how much bigger, but you can see this is going to be a little bit closer, right? So if this were something that I was going to do by hand, especially if I didn't have access to a calculator, this midpoint method might be really helpful. Okay? Now, I will tell you that for any method that we use, no matter whether it's the right endpoints or the left endpoints or the midpoints or really any other point, to make it more accurate, we can always do what? Add more rectangles. So whichever of those methods we use, we can always add more rectangles. And that would make it more accurate. All right? Now, I heard somebody say something about slanted. Who said that? Did you? Okay. What if we did this? Instead of using the right endpoints or the left endpoints and using rectangles, we could find the area of these shapes right here. What shape is this? Trapezoid, right? So we could find the area of these trapezoids. For this particular one, this looks like it's going to be really close, doesn't it? Okay, now, I didn't draw this perfectly well. All of these, the tops of the trapezoids, all of the tops of the trapezoids are actually going to be a little bit above the line. Anybody know why it's going to be a little bit above? Because of the curve. It's concave up or down? It's concave up. So it's concave up. These secant lines, that's actually what they are. These secant lines are going to be above the curve. So this would be a little bit of an over-approximation. But it's a lot closer than those rectangles, right? Yeah. So this is going to be an even more accurate way to do it. And it's something that we could do. Because we know how to find the area of a trapezoid, right? All right, so there's 4 different methods that we just went through there. We had left rectangles. So when I say left rectangles, we're drawing rectangles where the left endpoint of the interval gives us the height of the rectangle. We have right rectangles. We have midpoint rectangles. And then we have trapezoids. And we're gonna look at all 4 of those methods today. And the important thing to understand, and this is what's going to allow us to go from approximating using these shapes to finding the exact value, is that the more and more rectangles we add, what's going to happen? The closer to the actual answer we're going to get. And what we need to understand, too, is that it doesn't matter which one we use, and this is going to be really important. I'm going to use the right endpoints here to demonstrate this. But it doesn't matter which one we use. If we add more and more rectangles, it's going to get closer and closer to the value, the actual value, so close that it's actually going to reach the actual value when the number of rectangles is infinite. And that's going to be the key. That's going to how we're going to go from an approximation to the exact answer, is we're going to use infinitely many rectangles. Sounds like a lot, doesn't it? A lot of rectangles?